Hello everyone, welcome to the fifth chapter. This will be the final chapter of the mathematical reasonings playlist, or logic as we are calling it. And we have been looking at quite a few definitions, few techniques of. Let me write down whatever we have learned. We have learned what is and, what is for, what is or, what is for all these symbols we have looked at, and there exists symbol. We have looked at the meanings accompanied by quite a few examples for each one of these, and we also looked at what is P implies Q. In the previous lecture we looked at implications in quite detail, and I also mentioned terms like contra positive and converse of a statement. So contrapositive of a statement of essentially implies two statements, converse of an implies two statement. And I also mentioned something called the counter examples for disproving things. So without bothering too much about these definitions, today I plan to give you a few problems and solve a few problems with you that are exercise in logic. So I won't give you the textbook questions for making us understand the meanings of these, because we already have that, and that textbook questions we already, I think you guys can prove it yourselves. We are planning today to understand where these things are used in mathematics, why we study these, and where actually in real math we use these concepts, we use logic. So essentially we'll be doing proving problems. So we'll be doing 4 or 5 proofs today. So the first statement I'd like to write is, if A belongs to Z, which means if A is an integer, Z is a symbol that I often will use for integers, the script Z, script Z. If A belongs to Z, and so this is and we have learnt about, and 3A plus 1 is even, then A is odd. So there is an if something happens, then something should happen. This is statement of P implies Q type. And just pause the video, think about this intuitively, whether you can convince yourself that this is true or not, because even though I am saying prove, this is my heading, even though I wanted to prove these things, I first want you to essentially validate. Let us write it in black. Validate. What does that mean? That means that you'll have to check whether the statement is actually true or not. If it is true, then prove it. If it is false, then you'll have to disprove it somehow. So let us check whether this statement is true or not. So I hope that you have already checked a little bit. Let me walk you through how I check statements whether if it's true or not. So given A is an integer and 3A plus 1 is even, so we have to, if something satisfies both these criteria, it has to satisfy that A is odd. So take any A which satisfies these criteria. Well, take an integer A first of all. So maybe 5 can be an integer, and 3 into 5 plus 1, so this is 16. So this doesn't satisfy our criteria, because it does, I'm sorry. So 3 into 5 plus 1 is 16, which is even, so it satisfies the criteria. And what is the value of A? Well, A is 5. So take another example, say A is equal to 8, where A is not odd in this case. So A is equal to 8, and 3 into 8 plus 1 is 25, which does not satisfy our criteria, so this doesn't hold. This doesn't tell us about the statement we are making, because the statement we are making has to have these two criteria satisfied to begin with. So you take another, say 3, a is 3, so 3 into 3 plus 1 is 10. Am I right? So 3 to 3 plus 1 is 10, so 10 is even, and a is also odd. So it seems like the statement is true. Well, let us walk through it rigorously. I'll not rub this off, so let it be there, right? This will give us insight about the proof. So how do I prove something like this? If a is an integer and 3a plus 1 is even, so 3a plus 1, a is an integer say, and 3a plus 1 is even. What does something being even mean? It means that it is of the form 2 and it is some multiple of 2. So even numbers, saying something is even is the same as saying it is of the form 2k for k any integer, because any even number is a multiple of 2, so you can factor out a 2 and you can write it as 2 into k for some k in integer. So pause the video here if you are new to this kind of writing even numbers in this type, and think about it and then proceed further. So 3a plus 1 can be written as 2k. If 3a plus 1 is even as given in the question, then it can be written as 2k. And hence 3a can be written as 2k minus 1. I subtracted 1 from both the sides. And a can be written as 2k minus 1 over 3. Well, does this say a is odd or not? Because ultimately what we have to find, we have to establish whether a is odd. So does this say whether a is odd? I don't think so, right? So it leads us nowhere. So it suggests, even the intuitive work we have done here suggests something else about the statement. We have assumed what a is to begin with, right? Because a is an integer, we cannot have, this statement does not make any argument about 3a plus 1 being equal to 8, because then 3a would be equal to 7 and a would be equal to 7 by 3. So a is not even an integer. We do need an integer to begin with. So it cannot be any even. This essentially shows that we cannot start from the first statement. We have to start from the second statement somehow. A is odd. So what do we do? You assume that a is not odd. I am gradually leading to this method of proving. We established in the previous lecture using truth tables and whatnot that P implies Q is true, or is the same as, is equivalent to not Q implies not P. This result we established in the previous lecture even logically, and we verified it using the truth table. So now can we use that fact here, whether if a is even, so a not q here means a is not odd, and a is not odd means a is even, because a number can be either even or odd. So if a is even, what had happened? If a was even, then this turned out to be odd, then hopefully we'll get a result. So say that a is even, so which implies a is equal to 2k for some k. This k is different, so for some k. So what about 3a plus 1? 3a plus 1 turns out to be 3. This will be again an even number. 3a will be an even number because 2 into 3 into a, or k plus 1. So 3a plus 1 can be written as, this will be equality, 3a plus 1 can be written as 2 into 3 into k plus 1, because a is equal to 2k for some k. So which means that 3a plus 1 is an even number plus the next number to an even number. So 3a plus 1 is odd. And isn't that contradictory to the fact that 3a plus 1 is even? We have just shown that if 3a is even, then 3a plus 1 cannot be even. So we have just shown that if not q, then not p. So haven't we shown p implies q? Haven't we shown this is correct? And I also use the word contradictory to the fact that 3a plus 1 is even. So I use the word contradictory. So this should suggest something. There is some similarity between proving the contrapositive of a statement and proving by contradiction, which we are going to do next. So if you don't understand, just hold on for a little while. In the next problem we'll see. So I hope this problem is clear. Pause the video, try to understand it properly, and then go forward. So the second statement at hand is, if n is odd, I am not writing if, so I'll write implies to. If n is odd, n square is odd, right? This is something I have to prove or disprove. So I hope you have thought about this already after pausing. And now let us see. So if n is odd, take any odd number and square it. Well, it seems like it should be odd because odd times odd is odd, right? So that's one way of proving it. So one way of proving it would be in writing, right? If the square of an odd number, okay, I'll write it in, wait, actually these colors are not visible here. If n is odd and n square then would be n times n, which is odd times odd, which is an odd number, because any odd times odd will be an odd number. Even then that we have to prove. So n square is odd, but this is not a very rigorous way, right? But this gives an intuition whether the statement is true or not. It seems like it is true. So let us prove it mathematically. So assume that n is odd, because P implies Q means when P happens then Q should happen. So we assume that P happens and Q doesn't happen, right? And not n square is not odd. That is, n square is even. So isn't this very similar to the previous thing what we have done? So we have assumed P somewhere. We have assumed P. So assume a is an integer and 3a plus 1 is even. Then we have produced this fact, 3a plus 1 is odd, contradictory to the fact that 3a plus 1 was even, and hence we concluded that P implies Q. So similarly, here we are assuming n is odd to begin with, and n square is not odd, that is, n square is even. Because of the previous argument we gave, a number can be only even or odd. It cannot be both or it cannot be neither. So does this lead to some contradiction to P, to n being odd? Well, let us see. What if n square is even? If n square is even, then it can be written in the form 2k, and n is odd means n is actually written in the form of 2k, some I'll take 2a if you want, or 2k dash plus 1, because this is an odd number. So 2k dash plus 1 whole square is written in the form 2k. Is it possible? Let us see. So this is actually 4k dash squared plus 4k dash plus 1, which is actually 4 times some k dash square, okay, anything 4 times something of the first two. I have taken 4 common from the first two expressions, so let us just write it down. 4k dash square plus k dash, I shouldn't rush ahead, and plus 1. Can it be equal to 2k? So do we see a problem here? The thing on our left is some even. For multiple of 4 means it's a multiple of 2. It can be written as 2 into 2 into k dash plus k square. Some even number plus 1 is equal to some other even number. Can it be true? The left side is odd, the right side is even. So instead of reaching a contradiction to P, instead of reaching not P, not Q implies not P, we have reached a contradiction, that is the assumptions in mathematics are being contradicted. So assumption to the fact that a number is either even or odd is being contradicted. So this is called proof by contradiction. Proof by contradiction. So actually we are not contradicting the fact that P is happening. We are not contradicting the fact that n is odd. As in this case, we have contradicted our assumption. Here we are contradicting just some assumptions in mathematics, and this is the symbol we use. Often mathematicians scribble this, and we use this for arriving at a contradiction. So we are contradicting some other fact. So but one should see the similarity between the contrapositives and contradiction. It's very important for us to notice this. People often avoid this. People never talk about this, but this is very similar. So I'll write very similar to contradiction. Contradiction. So now I encourage you to please go and look at a lot of mathematical statements of P implies Q form. Try to prove it or disprove it. You can find them in your textbook, or you can find them online, wherever you do. But just go through the logic of what is contrapositive and what is contradiction, and you'll be amazed at how similar these two are, but these are taught in two completely different manner. So the next problem we have is the equation. This is another statement. We'll have to prove or disprove, or we'll see. So the equation x square equal to x square minus 1 is equal to 0 does not have a root lying between, this is the shorthand we have writing, between 0 and 2. So this equation x square minus 1 equal to 0 does not have a root lying in between 0 and 2. So 0 and 2 on a number line. So the statement says that there is no root in this region. So is this statement true or false? How do we prove it or disprove it? Think about it. Well, you don't need a lot of knowledge about quadratic equations to solve this equation, right? So x square equal to 1, on adding 1 both the sides, we get x square equal to 1, and from this we get, so what number squared is 1, so minus 1 or plus 1. So both can be our roots. Even if you square minus 1, it will give you 1. Even if you square 1, it will give you 1. So we immediately see that this 1 lies in between 0 and 2, right? It lies exactly in between. It's the midpoint of 0 and 2. So immediately the statement is proven wrong, and we are interested in now noting how we proved it wrong. We gave an example. We gave an example of one root. So x is equal to 1 is a root. And we gave the example of x is equal to 1 that lies between 0 and 2. So we gave an example of the statement not happening in one case. So this example is known as counter example. We countered the statement using an example. So we gave a counter example. And we have disproved the statement, right? You cannot prove the statements using examples, as we studied here, I think. So this is just an example of a is equal to 8 was just an example where the statement okay, so a is equal to 5 would be an example where the statement held true. And we couldn't have stopped with this because this is just an example. It just shows you that for a equal to 5 the statement is true. But this counterexample, what does it do? It shows that I am suggesting that the statement is true, but I have shown an example at a place where the statement is false, and hence I have disproved the statement. So for proving results, you don't give examples. For disproving results, you give counterexamples. You don't memorize the statement that I just made, but think about it and understand. So since I have time, I'll do 2 more, I think. These are small questions. And just notice how many places we are using logic here. Logic that we learnt. Right? In the next example, it will be even better. So say that x square is equal to 4 and x square equal to 4 implies 5x equal to 10. So, is this true? If so, then prove. If it's not true, then disprove. So x square equal to 4 implies 5x equal to 10. I can say that x square equal to 4 means x is equal to 2, and with this would imply that 5x, that is 5 into 2, is equal to 10. This holds true. But again, notice that I have given you one example of such root for which 5x is equal to 10 is true. But to prove formally that x square equal to 4 implies 5x is equal to 10, what do we have to do? We have to look at all possible cases where x square is equal to 4. So x is equal to minus 2 is also a root. So minus 2 or plus 2. So for x equal to minus 2, 5x is not equal to 10. So 5x is not equal to 10, which means that this statement is incorrect. We have disproved the statement using the counter example that x is equal to minus 2. But say that we had been given x square equal to 4 implies 5x is equal to 11. Well, then x is equal to 2 would also work as a counter example, because x is equal to 2 satisfies this, but it does not satisfy this, and hence this statement is wrong. Right? So you can disprove statements with counter examples. You cannot prove them. If the statement is you cannot prove them for now, right? Let's look at our last example of the lesson. After that, you have to solve many more examples, okay? And we might have separate textbook problem sessions, I don't know, but I think the lectures will be enough for you to go ahead and open your textbook and just start solving. Don't worry if you do not get an answer, but at least you should start. You should try out. So x is greater than y implies negative x is less than negative y, minus x is less than minus y. Well, this is very interesting because this last problem gradually, very sneakily leads you on to linear inequalities, which we'll be learning in much more detail in forthcoming lectures after set theory and relations. So try this problem. Well, just play with it. Start to just insert values and get an intuitive idea of what it means. So x is greater than y, so 5 is greater than 3, I know. Then is minus 5 less than minus 3? Well, yes, minus 5 is a bigger negative number, so it's less than minus 3. So what about other values? Maybe minus 7 is greater than minus 10. Then is 7 and 10, 7 is less than 10. So maybe intuitively, if you see, if this is a number line, if this is x, then x has to be greater than y. So x has to be on the right side of y, and say that we have 0 here where these two numbers are positive. So minus x would definitely be less than minus y, because minus x would be mirrored somewhere here, minus y would be somewhere here, and minus x is less than minus y. What if 0 was in between? What happens then? So say that this is y. Yeah, now we have a problem. So can you see the problem? Minus, okay, now still okay. Even if, well, I thought I had a problem, but I didn't. So even if this is 2 and this is minus 2, so this is minus 2, yeah. So minus of 2 would be somewhere here, and minus of minus 2 would be somewhere here. So again, minus 2 is less than 2. You try for x is equal to 2 and y is equal to minus 2. So you will see that this equation is satisfied. Of course, this has to be this, right? This is a very famous rule we learn. So now we have an intuitive idea of what is happening. Even if 0 were here, you should try out the negatives and you should try out this mirroring thing and get an intuition for it. Let us try and let us prove it rigorously now, mathematically. So P something implies something. So you assume that the P statement, the first statement, is true. You assume x is greater than y, and you assume that minus x is not less than minus y. So you assume the negation of minus x less than minus y. So how do we negate this? The negation of this would mean minus x is greater than or equal to, all the ways you can disprove that minus x is less than minus y would give us the negation. So if minus x were greater than or equal to minus y, then this would be false. I'll be negating this statement. So you can also verify that the negation of this statement would go back to this statement. This statement is actually minus x is equal to minus y, or minus x is greater than minus y. So it's a compound statement. If you negate it, you will get back this. So just use your logic there again and check. But intuitively, you don't even need to think about all these robotic procedures. You just trust your brain and just follow it. So now I have assumed that minus x is greater than equal to minus y, which would imply what? Y minus x. I am adding y to both the sides. So y minus x is greater than equal to 0. You can add things in inequalities, right? So if 3 was less than 5, no matter what quantity you are adding or subtracting to 3, if you do add and subtract the same quantity from 5, the inequality should remain unchanged. So 3 minus 2 should be less than 5 minus 2, or 3 plus 1000 should be less than 5 plus 1000. All this we'll learn it further, but still we're using it, and this is kind of intuitive also, so I didn't bother to, So y minus x is greater than equal to 0. What does this mean? This means that y minus x is positive, and something minus something, if it's positive, then this has to be greater than this. So y has to be greater than x, right? But what have we assumed? X is greater than y. So are these statements opposites of each other? Are these statements negations of each other? Well, no, but these cannot happen at the same time. These are not negations of each other, because x is greater than y, the negation will be y is greater than x, the negation will be y is less than or equal to x, but here y is just less than x. Anyway, these two sets are nothing in common. And excuse me if I am using terms like sets and inequalities again and again. The more you start going into the subject, the more you'll come back and learn these things more easily. So don't worry about it too much, just think about what I'm saying. Right, so y is greater than x, and hence it is contradictory to the fact that x is less than y, hence I have shown not p. So not q implies not p is what we have shown here, which means p implies q, which means this inequality is correct. So if this was confusing, you should watch it again, think about it, and slowly, with a calm mind, you'll be able to understand. So I think that's it for these lectures. I have done everything I had to. So let us meet quickly in the next lecture series, that will be on set theory and relations. Now we have quite a few logic to go forward in our mathematics, this high school mathematics. So let us meet soon. Hope you like the playlist. Thank you.